IBM and Google are two of the most influential players in the development of quantum computers. Both companies approach quantum computing with serious long-term commitment, massive investment, and strong scientific teams, yet their strategies, priorities, and design philosophies differ in important ways. In this video, we will compare IBM and Google quantum computers, explaining how they are similar, how they differ, and what their approaches reveal about the future of quantum technology. At a high level, both IBM and Google focus on gate-based quantum computing. This means they build quantum processors based on qubits, quantum gates, and circuits, rather than specialized approaches like quantum annealing. Both rely on superconducting qubits cooled to extremely low temperatures, close to absolute zero, to preserve fragile quantum states. Despite this shared foundation, their goals and methods diverge. IBM has placed strong emphasis on accessibility, ecosystem building, and steady scaling. Google has focused more on experimental breakthroughs and pushing the limits of what quantum hardware can demonstrate. IBM was one of the first companies to make quantum computers accessible to the public through the cloud. Its IBM Quantum platform allows researchers, students, and developers worldwide to run experiments on real quantum hardware. This open-access approach has helped create a large global community and positioned IBM as a leader in practical quantum education and experimentation. Google, by contrast, has taken a more closed and research-driven approach. Its quantum hardware is primarily used internally and through selected collaborations. Google's focus has been on achieving landmark scientific results rather than broad public access. One of the most well-known moments in quantum computing history came from Google in 2019, when it announced a demonstration of quantum supremacy. Google's quantum processor completed a specific task in minutes that was estimated to take classical supercomputers an impractically long time. This experiment was designed to show that a quantum device could outperform classical machines for a well-defined problem. IBM responded by questioning the classical benchmarks used in the claim, showing that improved classical methods could reduce the gap. This exchange highlighted an important difference in philosophy. Google emphasized proof-of-principle breakthroughs, while IBM emphasized careful benchmarking and practical relevance. In terms of hardware scaling, IBM has published detailed roadmaps outlining how it plans to increase qubit counts over time. IBM has consistently delivered processors with growing numbers of qubits, while also improving connectivity and coherence. Its strategy focuses not just on adding qubits, but on building a full-stack system, including software, compilers, and error mitigation tools. Google has also made significant progress in improving qubit quality, coherence times, and gate fidelities. Rather than publishing long-term commercial roadmaps, Google emphasizes solving fundamental challenges such as error rates and scalability, aiming to reach fault-tolerant quantum computing. Error correction is a key area of comparison. Both companies agree that large-scale quantum computing will require robust quantum error correction. Google has published influential research demonstrating logical qubits with improved error suppression, signaling progress toward fault tolerance. IBM, meanwhile, integrates error mitigation techniques into its software tools, allowing users to work productively even with noisy devices. Software philosophy is another point of contrast. IBM has developed a comprehensive open-source software ecosystem, including programming tools and simulators designed to make quantum development accessible. This reflects IBM's view that quantum computing will evolve alongside classical systems, requiring widespread adoption and experimentation. Google's software efforts are more tightly integrated with its internal research and long-term goals. Rather than focusing on immediate developer adoption, Google concentrates on building the foundational capabilities needed for future large-scale quantum applications. Commercial strategy also differs. IBM positions quantum computing as an emerging enterprise technology. It works with businesses, universities, and governments to explore use cases in chemistry, finance, logistics, and materials science. IBM's message is that quantum computing will become a practical tool through gradual, measurable progress. Google takes a longer-term, more exploratory view. Its quantum efforts are often framed as part of fundamental science and future technology rather than near-term commercial deployment. Google's approach mirrors its history in other fields, where breakthrough research eventually leads to transformative products. In simple terms, IBM focuses on building a usable quantum ecosystem step by step, while Google focuses on pushing the scientific frontier as far as possible. One emphasizes reliability, access, and integration. The other emphasizes bold experiments and fundamental milestones. Neither approach is inherently better. Quantum computing is still in an early stage, and success will likely require both strategies. Breakthrough experiments validate what is possible, while practical platforms turn those possibilities into usable tools. Looking ahead, both IBM and Google aim for the same ultimate goal: fault-tolerant quantum computers capable of solving problems that classical machines cannot. The path to that goal is uncertain, and different approaches increase the chances of success. The comparison between IBM and Google quantum computers is not about winners and losers, but about complementary visions. Together, they show how quantum computing is advancing through both careful engineering and ambitious experimentation. As quantum technology matures, the influence of both companies will shape standards, expectations, and applications. Understanding their differences helps clarify where the field is today and where it may be heading. In the end, IBM and Google represent two sides of the same effort, turning the strange laws of quantum mechanics into reliable computational power. Their competition accelerates progress, and their combined contributions bring the quantum future closer to reality.